Briefly, the substitution method involves solving for one of the variables using one of the equations, and then taking that equation and making a substitution into the other one. Because the y in the second equation here has a coefficient of 1, that would be the easiest variable to get by itself out of all of the options for this problem. So we're going to go ahead there and use equation 2 and just subtract 2x from both sides. That'll get y by itself. We get y equals 1 minus 2x, or you could write that as negative 2x plus 1. But the substitution part of this method is that now I'm going to take that expression, which we're saying is equal to y. We're going to take that and substitute it in that first equation for the y. So where we see that y there in the first equation, we're going to replace it with 1 minus 2x. So going to equation 1, we have 3x plus 2 times 1 minus 2x equals 4. So the benefit of doing that is that now this equation only involves one variable, x, instead of both the x and the y. So we're going to go ahead and distribute the 2 and combine like terms. So we've got 3x minus 4x, that's negative x. Then we can subtract 2 from both sides. Get negative x equals 2, and divide by negative 1. And we get x equals negative 2. Now because our system originally has both an x and a y in it, our solution needs to specify a value for both x and y. We typically give that as an ordered pair, x comma y. So what we have done so far is we have figured out our x coordinate. We also need to know the corresponding y coordinate. To do that, we can plug a negative 2 back in for x into either of those two original equations, or we can use some of the work we've already done and plug it in right here where we got y by itself already. We have y equals 1 minus 2x. Now that we know that x is negative 2, y equals 1 minus 2 times negative 2. So that's 1 plus 4, which is 5. So our ordered pair solution, the x coordinate is negative 2 and the y coordinate is 5. And we could take that and plug it back into both of the original equations to make sure that we get true statements showing that it does in fact satisfy the system.